So this right here is the definition of the extension, All right. And, all right. And he says, if you have P of X and F of X is irreducible, right? And he says P prime of X equal to basically his just phi of P of X. Right? So let P prime of X be the corresponding polynomial given by the map over an F prime of X. He says the isomorphism phi maps the maximal ideal P of X to the maximal ideal P prime of X. So the ideal is also maximal. He says basically here, since P of X subset of F maximal it implies that phi of this thing, which by the way is this thing, like is subset of and that follows from the theorems we have on the image of a subring, the image of an ideal being an ideal, and so if they're and the inverse image of an ideal being an ideal. So if you assumed F prime, if you assumed this was not maximal, you could look at the inverse image of that ideal, and it would give you an intermediate ideal between the ideal generated by P of X and F of X itself, which then would contradict the maximality of the P of X ideal. It's something like that. That's the kind of argument that can be offered. Or maybe you've already proved the theorem that an isomorphism maps a maximal ideal to a maximal ideal in this sense. Nevertheless, it is true. And so what does that mean? Well, that means that so what's that mean? That means that P prime of X is irreducible in F prime of X. Right? All right. And so then what? So it says the following theorem then shows that the fields obtained by adjoining a root of P of X to F and a root of P prime of X to F prime have the same algebraic structure. So here it is. So this is theorem 8. He's like phi mapping from F to F prime, right? And I guess when he puts a tilde like this, that means an isomorphism, right? Isomorphism of fields. And let P of X be irreducible. In F of X and phi of P of X equal to P prime of X in F prime of X. So that's the irreducible image of it, right? Then, again, obtained as we described right above the theorem. He says let alpha be root of P of X equals to 0. In other words, P of alpha equal to 0. Let beta be root of P prime of X equal to 0, meaning that P prime of beta equal to 0. All right. Then there is an isomorphism. Sigma, mapping from f of alpha to f prime of beta. And it's given by simply mapping alpha to beta and extending naturally. So in other words, alpha maps to alpha, alpha squared maps to beta squared, 1 maps to 1. You can build the formula from that. And he says, okay, well, this extension theorem will be of considerable use when we consider Galois theory later. Because you can kind of picture it. I'll draw the picture over here. So we have sigma, we've got f of alpha, f of beta, like this, right? And those are over, that's over f. That's over f prime, right? And so down here, we have the original map phi. So this essentially says that the isomorphism of fields lifts to an isomorphism of extensions in this natural way.
Okay, that's cool.
Yeah. Now the proof of this is given on page 519. And let's see, I'm trying to see if there's anything. It really is, I'll try to explain it in words. It really just is the following thought, which is that, okay, so this is isomorphic to f of x mod p of x, right?
And then that would be f prime of x.
But that is isomorphic to f prime of x mod p prime of x. And then that is isomorphic to that, so therefore this is isomorphic to that. I think that's essentially the...
No, it's quite cool.
Yeah. So the next section is on algebraic extensions. So that's where we have like the degree times degree formula and all that stuff. So I will try to be faster through that section. But we do need to state the theorems. Trying to think what comes after that. But anyway, we're doing fine. It's just, we really do need to say these things this semester. Otherwise, if I just try to like skip past them, we'll have lost track of what we're doing,